Hey guys, in this video, I'm going to talk a little bit about Newman projections and kind of how to go about attacking problems where we either have to convert from line angle to Newman or Newman to line angle, because this is kind of the first introduction of viewing molecules in a different kind of, I guess, projection. We have the Newman and the Fisher, which are kind of the two main ones that we'll deal with. This is a very foreign concept, I think, and at the beginning it can be really daunting, but kind of having a good view on how to convert from line angle to Newman and Newman to line angle will really help you understand kind of some of the potential energies of conformational isomers. Um, so kind of first off, I want to talk a little bit about like what really are conformational isomers. And the way that I really think about it is the atom connectivity is the exact same, but they're just kind of rotated about a bond. So, if I have my hands like this, but I rotate my hand to be like this, nothing about my hands has changed, but just kind of the way that they look in relation to one another has changed. And so when we rotate about bonds, we also change the potential energy stored within a bond. So for example, like if you have two magnets right here, and if you bring the magnets up, you haven't really changed any properties of the magnets, but you've kind of created potential energy and you've created strain within the system. If you stand like this and then you put your arms up, nothing about your arms or body has changed, but your arms now have potential energy. And that's kind of a little bit of an explanation as to why when we get these eclipsed conformations, there is increase in potential energy. So I'm going to try to go through a few problems, and it really kind of helps to view this if you have a molecular modeling kit. But I understand that not everyone does. So I have a molecule here that we can try to kind of use as a model, but there are some limitations, obviously. But I will try my best. So I think that another area of confusion is some people think that there's only like one definite answer, but again, with these written exams, there are multiple ways that you could format your answer, and you could rotate the entire thing and nothing about it really will have changed, and I'll show you what I mean. But so you can really either look at the bond. So I'm just going to go ahead and start with this molecule. So this is some made up molecule that I just made. And if you can see, we have it in a staggered conformation. So if we were to have all of the groups kind of overlapping, that would be eclipsed because they're kind of eclipsing one another. You can see the red is being eclipsed by the blue. But when we twist this carbon, it's no longer eclipsed. So we don't change anything. It's kind of hard to see, but I'm not changing anything about this carbon right here, but I'm rotating this back carbon. And so if you can see, that's kind of a visual of what we want to see. So in this case, we again are in a staggered conformation. So we want to look down kind of the barrel of the bond. So we have our molecule here and we want to change our perspective. So we're staring at the carbon-carbon bond. So it would be something like this. In your guys' case, you would want to see this because the front carbon, which would be kind of what the legs are, would be this carbon. And because we kind of have like the upside down Y, we know that this needs to be the front carbon. So in the example that we have, if we're taking the red's point of view, we can see that if we're looking at it like that, we have a NH2 group coming at us. When we change our perspective, so in this case, for me, it's going to be a little hard for you guys, but I'll try to, let me see. I think it's shifted. Yeah. So right now, this orange is coming at you. So when you change your perspective to be something like this, this is on your right. I'm not sure if it's mirrored, but it's on your right. Take my word for it. So this is the NH2 group. You change your perspective and now it's on the right. So in our red world, NH2 goes on to the right. And that leaves the CN group on the left. And above we have a methyl group. So now we're still looking at it like this. And so this should be on your left. But so whatever was coming away from you will be on your left. So in this case, the bromine will be on the left. And the chlorine will be on your right. And then you have another CH3 group down. And so whatever was on a wedge for the front carbon, if that's on the right, whatever's on a wedge on the back carbon should also be on the right. So we have an NH2 on a wedge, it's on the right. Chlorine, it should be on the right as well, just as a way to like double check your work. And then so we can then kind of swap the point of views, and I'm gonna not use the molecule because it's very hard. I don't know if Zoom will flip it, but so hopefully you guys can start to visualize in your head, you know, the molecule in front of you, you change your perspective. So now if we take the orange point of view, what was going into the page before, when we look at it now, will be on our right. So the bromine will be like that. Chlorine will be on the left, CH3 group on the bottom. And then, so on the back carbon, now we have the NH2 and the CN and the CH3. So the CH3 is going to be up, and then what was coming at us now will be on our left. So it will be the NH2 and the CN. And so we should kind of have the same groups on the same side. So like here we have the Cl and the NH2 on the same side, and here we have the same thing. Bromine and the NC, or the CN, bromine and the CN. So that's another way. Like these are the same molecule, just a different way to view them. And one more note, because I think that sometimes people get a little bit confused, but if we basically take this entire thing right here, we can almost rotate it so that it's looking kind of like this, where we have almost like the front carbon being a Y. And, you know, if we have something like this as our answer, that will also be correct, because kind of going back to what makes a molecule identical, we didn't really change anything. We just rotated it slightly. So now I'm going to turn this back. So I'm just going to do kind of this for the first one, but I do kind of want to talk about how we can rotate one of the carbons to create an eclipsed conformation. Again, I'm only just going to do it for one because we could do it for all of them, but that would just be a lot of time. So if we take we'll just take the back carbon. Remember, the back carbon is what's kind of represented by that ring. If we turn it clockwise 60 degrees, I'm sorry, 120 degrees. No, yeah, 60, sorry. That way we'll get the eclipsed conformation. So I'm going to go ahead and draw that. So we didn't touch the front carbon. So the front carbon stays the same. And now we have rotated the back carbon. So now we kind of go in and add that. So you can see that the kind of relative position of all of these molecules are the exact same. So it's really important that, you know, if you go one position clockwise, we go from bromine to chlorine. If we do that again, we should again have bromine to chlorine. And we go chlorine to methane, chlorine to methane, methane to bromine, methane to bromine. So that's kind of a way that you can double check, because we don't want to change the absolute configuration. So what the back carbon was an R or an S configuration, when we just rotate it, it should remain an R or S, whatever it was. And that's kind of what checking the one position clockwise will do. So you can kind of rotate by 60 degrees, 120 degrees, but you know, practice with that. See if you can kind of come up with all the staggered conformation and all the eclipsed conformations. And so kind of going back to the conformational isomers and the rotations about the bonds, when we have two big groups eclipsed, we're going to have a lot of strain. So for example, if we have a group or a projection like this with we are going to have a lot of strain coming from these two eclipsed groups because they're both pretty bulky. And when we try to rotate them, they're going to fight each other because we want to remember that the electrons are in electron clouds. And so it's kind of like with that magnet, you're putting two negative charged electron clouds close to one another. And so they're going to want to repel. And so if you're trying to reduce the torsional strain, you want to have, as small groups basically as possible overlapping, and you don't want to have big groups overlapping. So this video, I really just wanted to talk about the Newman projections rather than the kind of energetics behind them. But if you guys want me to kind of make a short other video for that, I can. But just for this video, I'm going to kind of refrain from that and just stick with the Newman projections. So for the second one, I just want to convert line angle to Newman. And so you kind of have some choice here. I want to look at this bond though. That's kind of really like the only one to look at with Newman. So you can theoretically take either of these two approaches. But I'm just going to go ahead and do the one in purple. So we know that there's going to be a hydrogen here. And so we want kind of the upside down Y that looks like this, because the first carbon we see has two legs on the bottom. If we were to take the green's point of view, we would want the Y because the first carbon we see has kind of like that Y shape. So we can, when we're looking at it, the hydrogen is on our left because it's going into the page. We change our point of view, hydrogen's on the left, chlorine's on the right, and we have this ethyl group. And then on the back carbon, bromine's on the left, again, because it's going into the page, hydrogen's on the right, and the CH3 group is on the bottom. So you could, again, do this with the green. You should get the same molecule, but it may just kind of be flipped. The front and the back carbon will basically just, you'll take it and you'll flip it. Just like with the pancake flip from the identical molecule video. And so now we want to convert a Newman to a line angle. And the way that I like to do this is I first draw the kind of backbone of the carbon bond that we're looking at, and then go in and fill everything out. And you may have to like rotate it a little bit at the end, but I just kind of always start with the bond being horizontal. And then we see that I will take this point of view. So on top, we have a CH3 group, and on our right, we have a bromine, and on the left, we have a chlorine. So again, we should be able to take the molecule, put it in front of us, change our perspective, and kind of get back to the Newman. So on the back carbon, which would be this one, we have an ethyl group on the bottom, so it'll be like that. And then we have a hydrogen on the right and a ammonia group on the left. So it will look something like that. Let me make that a little bit clearer. Like that. So again, double check your work, take the molecule, go to Newman, make sure they check out. And so this last example, I just wanted to throw this in there because there could be a scenario where they don't necessarily give it to you written out like this, but they'll give you kind of the line angle. And so don't be alarmed if they do that because it's basically the exact same thing. It just almost makes it easier. So again, start with the kind of bond that we're looking through. And then on the top, we have a hydrogen. On the right, we have a chlorine. Again, I'll take this point of view, sorry. And then on the left, we have a methyl group. And on the bottom of the back carbon, we have a fluorine. On the right, we have an isopropyl group. And on the left, we have a propyl group. Something like that. So those are kind of the most common questions I've seen. I have seen one, I'm not going to work it out. I'm going to kind of leave it to you guys, but I have seen it where they almost put two Newmans next to each other. And they'll be like connected like this. And you kind of have to figure out, what does that molecule look like? And so you kind of go through the same exact process, but you are just kind of looking two molecules dead on. So see if you can, this isn't really a proper example, but I think there may be one in the workbook or the worksheet or the practice exam. You won't be able to miss it, honestly. Like, it looks really daunting. So if you see that, try to work it through. And if you have questions, post on Piazza, or if you have any questions about any of this, post on Piazza or group me, and someone will help you out. But good luck.